What if Mars had Earth's atmosphere? Mars. The red, dusty, frozen wasteland that humanity has dreamed about for over a century. We've sent rovers across its surface. We've mapped its canyons, its volcanoes, its ancient riverbeds. We've even started planning missions to send humans there within our lifetime. But there's one thing standing between Mars and becoming humanity's second home: its atmosphere. Today, we're going to run a thought experiment. What if, in an instant, Mars's atmosphere was completely replaced with Earth's? Same pressure, same oxygen, same nitrogen mix we breathe every single day. Would Mars transform into a lush, second Eden? Would humans be able to walk outside without a spacesuit? Or would something far stranger, and far more dangerous, happen? Stick around, because by the end of this video, you'll understand not just what would happen to Mars, but what it would take to actually make this dream a reality. Let's get into it. Section 1. Mars as it really is today. Before we change anything, we need to understand exactly what we're dealing with. Mars's atmosphere is almost nothing compared to Earth's. Its surface pressure is less than 1% of what we experience at sea level. To put that in perspective, standing on the surface of Mars right now is roughly like standing at an altitude of 35 kilometers above Earth, nearly 3 times higher than commercial airplanes fly, and well above where the Armstrong limit is, the altitude at which water in your body would boil at normal human body temperature. And what little atmosphere Mars does have is almost entirely carbon dioxide, about 95% of it. There's only a trace of nitrogen, a trace of argon, and virtually no oxygen. The temperature swings are brutal. During the day, near the equator, it might reach a relatively pleasant 20 degrees Celsius. But at night, temperatures can plummet to minus 90 degrees Celsius or lower. There's no thick atmospheric blanket to trap heat, so the planet loses warmth almost as fast as it gains it. Then there's the radiation problem. Earth is protected by two things: a thick atmosphere that absorbs and scatters harmful radiation, and a global magnetic field that deflects charged particles from the sun. Mars has neither in any meaningful sense. Cosmic rays and solar radiation bombard the surface constantly. Astronauts on Mars, even for a relatively short mission, would absorb significantly more radiation than what's considered safe for a lifetime on Earth. And because the atmospheric pressure is so low, liquid water simply cannot exist on the surface. It's not that Mars is too cold for liquid water, it's that the pressure is below what's called the triple point of water. Any liquid water exposed to the Martian surface today would either freeze instantly or boil away into vapor, sometimes doing both at once. This is why Mars looks the way it does: dry, dusty, seemingly dead. But here's the fascinating part: it wasn't always like this. Evidence from rovers like Curiosity and Perseverance, along with orbital imagery, strongly suggests that Mars once had a thicker atmosphere, flowing rivers, lakes, and maybe even an ocean covering part of its northern hemisphere billions of years ago. So the question isn't really, can Mars support an Earth-like atmosphere? It's what changed, and can we reverse it? That's exactly what we're about to explore. Section 2. The Atmosphere Swap, Immediate Effects. Let's run our experiment. In an instant, Mars's entire atmosphere is replaced with Earth's 78% nitrogen, 21% oxygen, and trace gases at sea level pressure. The first thing that happens is pressure equalization. Instantly, the crushing near vacuum of Mars is replaced with breathable, thick air. Sound would travel far more efficiently than it does on Mars today, where the thin atmosphere makes everything eerily quiet. Clouds, real, fluffy, Earth-like clouds, would begin forming for the first time in possibly billions of years. But there's an immediate complication: gravity. Mars's gravity is only about 38% of Earth's. Atmospheric pressure depends partly on the strength of gravity holding gas molecules down. So even with the same mass and composition of air Earth has, that atmosphere would behave differently on Mars. It would extend higher, forming a taller, more diffuse column of air above the surface, roughly 2.5 times taller than Earth's atmosphere for a similar mass of gas. Next comes the temperature shift. A thicker atmosphere means a stronger greenhouse effect. Water vapor and any residual carbon dioxide mixed with the new air would trap solar heat far more effectively than the old thin Martian air did. Average global temperatures would begin rising, not overnight, but steadily. Polar ice, which is a mix of frozen water and frozen carbon dioxide, would begin to melt and sublimate. Then comes the moment scientists have dreamed about for decades: liquid water. With Earth-level atmospheric pressure, water can now exist as a stable liquid on the surface. The ancient river valleys and lake beds mapped by orbiters, like the massive Valles Marineris Canyon system, 4 times deeper and several times longer than Earth's Grand Canyon, could start to fill again. Imagine standing at the edge of a Martian canyon and watching, for the first time in geological memory, a trickle of water start to flow along its ancient path. The sky itself would change too. Today, Mars's sky appears a butterscotch or reddish-brown color because of suspended dust particles. With a thicker, Earth-like atmosphere and different particle scattering, the Martian sky could shift toward a pale blue during the day, though likely with a slightly different hue than Earth's, due to the residual dust and different atmospheric chemistry. Within days to weeks, Mars would look less like a dead world and more like a strange, red-tinted, high-altitude version of Earth. But this is where the excitement needs a serious reality check. Section 3. What would actually grow there? Let's assume, for the sake of imagination, that we either solve the magnetic field problem or simply enjoy this transformed Mars during that long transitional window before the atmosphere fully leaks away. What would actually be able to survive there? Plant life is the first candidate. Certain extremophile organisms on Earth, like lichens, cyanobacteria, and some species of algae, have already been tested in simulated Martian conditions in laboratories, including chambers that replicate Martian pressure, temperature swings, and UV exposure. Some of these organisms have shown surprising resilience, even under harsh simulated Martian environments. With a full Earth-like atmosphere added to the mix, removing the pressure and radiation problems, the survival odds would improve dramatically. Over time, if liquid water became stable and temperatures moderated, simple plant life could potentially take root near the equator and around the melting polar caps, where water would be most abundant. This could kickstart a very slow, very early version of a water cycle: evaporation, cloud formation, and rainfall, mirroring processes we take for granted on Earth. What about humans? This is the part everyone really wants to know. Could you walk outside on this transformed Mars without a spacesuit? The honest answer is, closer than ever, but not quite yet. With Earth's atmospheric composition and pressure, the biggest killer, instant decompression and lack of oxygen, would be solved. But Mars's lower gravity would still affect the human body over the long term, contributing to bone density loss and muscle atrophy, similar to effects seen in astronauts on the International Space Station. Radiation levels, while reduced by the thicker atmosphere, might still be higher than Earth's without that magnetic shield fully restored. And the day-night temperature swings, even with a thicker atmosphere, would likely still be more extreme than most places on Earth, given Mars's greater distance from the Sun. So realistically, early human visitors might be able to spend time outside with lighter protective gear, something more like high-altitude mountaineering equipment rather than a full pressurized spacesuit, rather than needing the bulky, fully sealed suits required today. That alone would be a monumental leap. Going from instant death without a suit to survivable with basic protection represents one of the biggest thresholds in making Mars genuinely livable for large numbers of people. Section 4. The bigger question: should we do this? This thought experiment isn't just science fiction, it's something real space agencies and scientists take seriously. NASA, ESA, and private companies working on Mars exploration have all studied various terraforming concepts. From artificial magnetic shields to releasing greenhouse gases trapped in the Martian regolith and polar caps to warm the planet naturally over time. But even in the most optimistic scenarios, most serious estimates suggest meaningfully transforming Mars's atmosphere would take anywhere from decades for the earliest changes to potentially centuries for a stable, breathable environment across large parts of the planet. And there's a deeper question worth sitting with: should humanity terraform Mars at all? If Mars once had liquid water and possibly even primitive life billions of years ago, could there be dormant microbial life still surviving underground today? Changing the entire planet's atmosphere and climate could make finding, and understanding, that potential life impossible. Erasing evidence of Mars's original history before we even get the chance to study it properly. It's a genuine ethical debate within the scientific community. Do we preserve Mars as a pristine scientific record of our solar system's past, or do we transform it into humanity's backup home? Maybe the real answer lies somewhere in between, carefully exploring and understanding Mars first, before we ever consider changing it permanently. Closing so, would giving Mars Earth's atmosphere turn it into a second Earth? For a while, yes, rivers would flow, clouds would form, and life might even take root. But without solving the magnetic field problem, it would be a temporary gift, slowly leaking back into space over thousands of years. The real challenge of terraforming Mars was never just about the atmosphere. It's about giving the planet back its heartbeat, a working magnetic field, a stable climate, and time. If you found this as fascinating as I did researching it, let me know your theory in the comments. Should we terraform Mars, or leave it as it is? And if you enjoyed this "What If," make sure to subscribe, because next time, we're asking, what if Earth had two suns?